Tonight we're going to take a look at nonlinear systems of equations. Last year we did linear systems of equations where we graphed two linear equations to see where they intersected to find the solution. Sometimes there was one solution, sometimes there was no solution, and sometimes there were infinite solutions. But we're going to take a look at nonlinear systems tonight. So first we're going to review the following systems of linear equations, and we're going to solve these by graphing. So we are going to graph the linear equation y equals negative 3x squared plus 4 and the equation y equals 3x minus 2. And I know they're linear because both x and y have an exponent of 1. So I'm going to graph this one in red. My y-intercept is positive 4. My slope is negative 3 over 1, so I should be going downhill. So it's down 3 and over 1, down 1, 2, 3, over 1, down 3, and over 1. And there is my graph of the line y equals negative 3x plus 4. So now I want to graph this one, y equals 3x minus 2. So my y-intercept is negative 2. It has a positive slope of 3 over 1, so it's up 3 and over 1, up 3 and over 1. And I can also go backwards, down 3 into the left one. And so there is my graph of the line y equals 3x minus 2. So if you recall, the solution was the point of intersection. So this is the solution to the systems of equations, and that point is 1, 1. So what that means is when I substitute in 1 for x, I should get 1 for y. And negative 3 times 1 is negative 3. Negative 3 plus 4 is a positive 1. If I plug 1 in here, 3 times 1 is 3, and 3 minus 2 is 1. So this is the only set of ordered pairs that will work in both equations. So let's go ahead and try the next two, which are not in slope-intercept form. So we need to put them in slope-intercept form. In the first equation, we have x minus y equals 3. So our goal is to get this into y equals form. So it will give us y equals x minus 3. Our y-intercept is 3. It's a positive slope, so that just means up 1 to the right 1, up 1 to the right 1. So there's the graph of the line y equals x minus 3, which is also, this would be in slope-intercept form. So 7x minus y equals negative 3. We want to graph that one as well, but we have to get that into y equals. So that turns into y equals 7x plus 3. So here again is our y-intercept at 3. It also has a positive slope, so down 1, 2, 3, 4, 5, 6, 7, and to the left 1. So this one has a very steep slope, so my line isn't that straight. But again, we're looking for one point of intersection. In this case, that's our solution, and our solution is negative 1, negative 4. So again, if I plug in negative 1 for x, negative 1 minus 3 is negative 4. If I plug in negative 1 for x here, 7 times negative 1 is negative 7, and negative 7 plus 3 is negative 4. So these two had just one solution, but if you recall from last year, if we had parallel lines, there was no solution, and if we had the same line, that was infinite solutions. So let's take a look at what that does if we're solving nonlinear systems. Okay, so in example 1, we have a linear equation, y equals x plus 2, and a quadratic equation, y equals x squared plus 3x minus 6. So let's graph y equals x plus 2 first. That's our linear equation. So I'm going to make my graph a little bigger so we can see it. So here is my y-intercept at positive 2. It has a slope of 1 Sorry, my tacos are ready. Okay, so there's the graph of our line, y equals x plus 2. So this is a linear equation, but we're going to see if we can get a solution when we have a quadratic equation. So on the quadratic equation, y equals x squared plus 3x minus 6. This one has a y-intercept of -6. If I find my axis of symmetry, so I'm going to find my axis of symmetry, it's negative b over 2a, which is -3 over 2 times 1. So my axis of symmetry is at 1.5, which is somewhere right here. So now I need to find my vertex. So if I plug in -3/2 into my quadratic equation, my y value, I get 8.25. So we're going to estimate, and I think I have my axis of symmetry on the wrong side, so let me erase that. My axis of symmetry is at -1.5, which is right here. Whoops, I'm erasing again. Which is right here, and then 8.25. So we know that this is 6, 7, 8. So it's supposed to be somewhere right about there. So since we know that this is the axis of symmetry, the points are equidistant, so I can graph another point right here. If I plug in 0, or if I find my, I'm going to plug in the point 1, and 1 squared plus 3 times 1 minus 6 is going to give me a -2. And again, since my axis of symmetry has points that are equidistant, there is my other one. Then I'm going to plug in the point 2. So 2 squared is 4, plus 3 times 2 is 6, and 4 plus 6 is 10, and 10 minus 6 is 4, and again, using my axis of symmetry. So here's my point, here's my axis of symmetry. It's 1, 2, well, it's a half, so let's start this way. It's 1, 2, 3.5 away, so I need to go, here's my half, and then 1, 2, 3, so my other point is going to be right there. That looks about right. Okay, so we're going to graph our parabola. Remember, it has a curve. So we're looking to see where the parabola and my line should have gone through here and the linear equation intersect. So my solutions are those two circles. My solutions are at 2, 4. That's this one right here. And at -4, -2. That's this one right here. So if I plug both of these solutions, 2, 4, into both equations, this solution is true in both equations, and -4, -2 is also true in both equations. Okay, go ahead and try number 2 on your own, and then check back for the answer. And then we will go over the video questions. Okay, so I graphed the line y equals -x plus 2 in green. So here's y equals -x plus 2. So x squared plus x minus 6, I factored it. I got an x-intercept of 2 right here and -3. My axis of symmetry was -b over 2a, which was -1/2. This is my axis of symmetry, and gave me a y value of -6.25. I also graphed the y-intercept at -6. Since the axis of symmetry is cuts the parabola into 2 equal pieces and makes it symmetrical, I know that if I just count over, use this axis of symmetry, here's -6, it's half a unit away from the axis of symmetry, so my next point is also half a unit away. Again, there's my x-intercepts. and then I just plugged in 3 for x, then I got 6, and using my axis with symmetry, my other point was over here. So if I circle our 2 points of intersection, one point of intersection is right here, and the other point of intersection is right here. So our solutions to this system of nonlinear equations, our solutions are at -4, 6, and 2, 0. So again, both of these will work in both of the equations. So we're looking for answers that will work in both equations, and since we have a linear and a quadratic, we're going to get 2 points of intersection sometimes. Sometimes, just like linear systems, we may not get any, or we may just get 1. Okay, so which ordered pair is the solution to the system's equations shown on the graph? So you're looking for the points of intersection. Which one of these points matches our points of intersection? And number 2, which ordered pair is the solution set of the system's equations y equals -x plus 1 and y equals x squared plus 5x plus 6? You need to find the ordered pair. So solve this system. You can solve it on your calculator. Find the point of intersection. And then enter it as an ordered pair. Be sure to put your answers in the Google form. Have a wonderful night. I'm going to go eat tacos.